So last time we have seen Rank-Nullity theorem. What was this? Suppose this is a linear map of vector spaces where dimension of V is equal to n. Then kernel A and image A are finite dimensional. And dimension of V, which is n, is dimension of kernel of A plus dimension of image of A. This dimension of kernel A, so kernel A is called null space of A head, and its dimension of kernel of A head is called nullity of A head. Yani kaç tane vektörü sıfıra götürüyor? Kaç tane linearly independent vectors? Image of A head in dimension of image of A head is called rank of it. Therefore, what we see from this is that dimension of V is equal to this dimension and this dimension. So, nullity of A head plus rank of A head. Yes. But this is if we have finite dimensions. Otherwise, this is not a number, and this case doesn't have to be numbers. They can be. As a corollary of this, I think I wrote the following. A linear map. Okay, so I had suppose this is a linear map. Dimension of these finite. Then the following is true. Then the following is true. Neydi onlar? EG üzerinden remote idi. Nullity of EG is 0, and rank of EG is dimension. Diyelim ki n olsun. So these are all equal to each other. We can do this. Aslında yani ispat etmeye gerek var mı? Çok emin değilim de. Dimension Evet, evet. Doğru. Conditioner bunlardan birisi.
Hayır, hayır.
Tamam. Evet. Evet, öbür türlü doğru değil zaten. Okay, so let's see. One implies two. Well, A is an isomorphism means it is one and onto, right? So if since A so I assume one, so it's an isomorphism. It's an isomorphism. It is one and onto, right? One and onto. In particular, kernel of A hat is zero, right? Is the zero vector space. One means kernel is zero. Bunu yaptık mı? Hatırlamıyor musun? Efendim? 116'da. Burada yapmadık o zaman, öyle mi? Okay. Böyle yazayım o zaman. İlk önemli is önce bu claim yapalım. Okay. So, proof of the claim. Sanki aklımda yaptık diye kalmış ama. Tamam. So, assume A hat is one. Okay. Ne göstermem lazım? Kernel A is empty, is zero. So must show kernel of A hat is zero vector space. Any subspace contains zero. Zero is in the kernel, but we have to show that kernel consists of zero vector only. So let's just choose some vector. Let B is in the kernel of A hat. Okay. Well then, this is zero, but we know that a hat of zero is also zero, right? Any linear map sends zero vector to zero, but then we see that a hat of B is the same as a hat of zero. Since a hat is one-to-one, and thus B equals zero because a hat is one-to-one. So what we have seen is that if you choose any vector in a hat, then it has to be zero. So it means in the kernel of a hat, we have only zero vectors. Zero vector space'in dimension'ını soruyorsun. Evet, o da zero dimension. Yani sıfır boyutlu olacak, evet. Tamam mı?
Dimension kernel A hat eşittir zero.
Burada söylediğim şey şu. Kernel of A hat sadece sıfır vektöründen oluşuyor. Onu söylüyorum. Evet. Bu sıfır vektörü. Şimdi bu tek yönü, değil mi? Here we have an economic statement. Now we have to do the other way around. Now assume kernel of a hat is 0. There is only 0 vector here. We must show a hat is 1 to 1. All right, so let's V1, V2 in V, so that a hat V1 is the same as a hat V2. Well, then a hat V1 minus a hat V2 is equal to 0. I just take this to the other side. But this can be written like this. A hat of V1 minus V2 is 0. But this means what? V1 minus V2 is in the kernel of a hat, which has only 0 vector. So this means V1 minus V2 is just the 0 vector, but that implies V1 is equal to V2. So if I have any two vectors so that the images are the same, then they are the same. Therefore, a hat is 1 to 1. Tamam mı? Peki, o zaman claim'i ispat ettik. This dimension what is it? A hat is 1 to 1. If it is 1 to 1, then kernel of a hat is 0. And that's this digit. So this implies nullity. Dimension of kernel of a hat. This is the 0 vector space and its dimension is 0. So we showed that 1 implies 2. Now let's see 2 implies 3. Tamam mı? 2 nedir? Nullity. So we assume the nullity of a hat is 0. But then by the theorem, so by the nullity, rank-nullity theorem, by the rank-nullity theorem, rank of a hat plus nullity of a hat is equal to dimension V, which is, let's say, n, but this is 0. We assume that nullity is 0. Therefore, so rank of a n is equal to dimension of V. Bu ne demek? So dimension of image of a hat is equal to n, which is dimension of W. Therefore, image of A is a subspace of W. You know that it's a subspace of W, right? Image of a hat is a subspace of W. But this subspace has the same dimension as W. Therefore, they must be equal. This implies image of a hat is the same as W, because this is a subspace. Değil mi? İki tane, bir uzayın bir alt uzayı varsa ve ikisi aynı boyuttaysa o zaman onlar aynı vektör uzayı aslında. Bu da ne demek ama? Evet, is on. Değil mi? Image is everything. Right? So, evet is on. Reklamın tersi yani. Bir reklam var ya, image is nothing diyor. Burada image is everything. Boş ver. Şimdi yok herhalde öyle bir reklam da eskiden vardı. Image is everything. Yok. Image is nothing. Neydi? Obey your thirst. Boş ver. Okay. So we proved that 2 implies 3. Now let's see 3 implies 100. Now we assume that rank of A is n. So assume rank of A is n, which is just the analysis of W, but this implies rank means that dimension of image of a head is the same as dimension of W, but since this is a subspace, it implies yes, so this implies image of a head is equal to this. Therefore, a head is onto. Okay. But on the other hand, nullity of A head is what? It is just dimension of B minus rank of A. But this is n, and rank is n. Therefore, this is 0. So nullity of A head is 0, and hence kernel of A head is just 0 to the space, so that A head is 1. So what we have seen is that A head is both onto and 1. Therefore, it's an isomorphism. That's A head is an isomorphism. Tamam mı? Yes.
There we say that if the dimensional kernel is 0, then it is 0. Can we have another vector which is dimensional 0, but not?
I didn't quite follow you.
We never found that dimensional kernel is 0, and we say that kernel should be 0 vector.
Okay. Well, if kernel was not the 0 vector space, kernel is a subspace. If it is not the 0 subspace, it should have at least one non-zero vector. But then it is dimension at least 1. Because if it is a non-zero vector, that vector is by itself linearly independent. You may find another linearly independent vector, or you may not find. If you cannot find another linearly independent vector, then it has dimension 1. If you can find some other vector, then it has dimension at least 2. But we know that it has dimension 0. So that cannot be any non-zero vector.
Then can say that the dimension is 0 and only the vector space is 0.
Vector space is 0. Yes. So for a subspace, space, let's say U of B, U is the zero vector space if and only if the dimension of U is zero. Argümanda yani zaten sıfırsa hani linearly independent vektör yok. Buradan sıfır. Ya da burada bu sıfır değilse en azından bir tane vektör var demek. Sıfırdan farklı bir vektör için. Dolayısıyla da hani ikisi aynı şey. Tamam mı? Soru soran var mı? Let's do one example. Okay. Okay. Consider the linear map. Let's say and from R3 plus 1 into ya da R3'den R3'ye gitsin. Given by, okay. And hence, so I have a triple, let's say X, Y, Z, and I have to tell you what the image is. Okay, let's say it is X minus Y and 2X minus 2Y. Okay, so determine kernel A head and image A. Well, determining a subspace means what? I have to either tell you what the elements of this subspace are, but that's not, of course, something feasible because it has infinitely many elements. But you can give a basis for the subspace, then you know that every vector in that subspace is just a linear combination of those basis elements. So determine the subspaces just comes down to finding basis for this subspace. So solution. Let's just find basis. Some basis. Tabii ki bir tane yok. Some basis for these subspaces. Okay. What about kernel, for example? Kernel of A hat. What is this? Well, kernel means what? The set of all triples so that A hat is equal to, right? So we are looking for X, Y, Z, so that this is the zero vector here. What is the zero vector here? It is just 0, 0. So if A hat is 0, then you know the formula for A hat. This implies X minus Y equals 0 and 2X minus 2Y equals 0. So this gives me just one equation actually. Just X should be 1. Okay. So kernel of A hat consists of triples so that X equals 1. Right? Kernel of A hat is a subspace of R3 and it consists of triples where X and Y are the same. And I can just go backwards, right? If x and y are equal to each other, then these are both 0, therefore this is 0. So something is in the kernel if and only if x equals y. Peki, x y'ye eşitse let's see how we can find the basis. Okay, so if x, y, z is in the kernel of a head, then x equals y, and thus this x, y, z is actually is just x, z, right? X equals y. And I can write this as follows, which is x, 0 plus 0, 0, z. And this is just x times 1, 1, 0 plus z times 0, 0, 1. So what we see is that any vector which is in the kernel can be written like this. A multiple of this vector and another multiple of this vector. Right? So can you guess a basis for the kernel? So guess, our guess is this. A basis for a basis data for kernel of a head is what? Nedir the basis? Evet, bir sıfır. Bir de sıfır. Bunlar kernel'da, these are in the kernel because x and y are the same, right? Same to be, x and y are the same. So they're in the kernel. So these are in the kernel. Base can the kernel because anything in the kernel, is a linear combination of these two, and this set is linearly independent, right? I have just two vectors, they are linearly independent because one of them is not a multiple of the other one. So this is our guess, but beta is indeed a basis for kernel and head because beta scans kernel of a head and its elements are linearly independent. So we have found the basis for the kernel. In particular, what is the dimension of the kernel? In particular, dimension of the kernel, the nullity of a head is what? Just 2, right? So nullity is 2. Which is 2. So what is rank of A? Rank of A. Well, it's just dimension V minus nullity, right? What is dimension of D? This is 3 minus 2, so this is just 1. So image of a head is one dimensional. Okay. Therefore, dimension of image of a head is just one. So it is a basis, and basis will contain only one non-zero vector. How can we find one such element? Can you give me a vector in the image? Efendim? 1, 2. Yes. So if you choose 1, 0, 0, you shouldn't give just an arbitrary vector in R2, but it should be an image, right? For example, 1, 2 is in the image, but 1, 3 is not in the image, right? So to find something in the image, just compute a head at some vector. So a head of 1, 0, 0. What is this? This is in the image because it is the image of a vector. And what is this? This is just 1, 2. So this is the image of a head. It's a non-zero vector. And I know that image a head is one dimensional. Therefore, this vector should constitute a basis for this space. Hence, let's say beta prime, which is that this vector is the basis. It's a non-zero vector, it's the basis for image of image. Yani o zaman ne görmüş oluruz? So image consists of vectors of this form, multiples of this. X coordinate, no, y coordinate is the twice the x coordinate, right? So image of a head actually vectors of this type. So some vectors, let's say lambda, and then it is 2 lambda, right? Lambda is a real number. Because this is the basis vector, so any vector in this subspace is a multiple of this, and multiples of these vectors, this vector are just coupled like this. Tamam mı? Soru soran? Yes.
We're going to say that for each lambda there is x, y, z in R. I mean, this is onto.
Onto what? Its image?
Yeah.
Well, it's by definition, it's onto. Right?
I mean, for example, for lambda, we need to equate x minus 1 to lambda, and for example, a tilde x, x minus lambda z is equal to that one. Do we need to state?
No. I know that image is one dimensional, right? So a basis for that subspace will be one dimensional. I mean, it will have only one element. And a basis, we know that just consists of, if it's only one vector, it should consist of a non-zero vector, right? So if you choose any non-zero vector in the image, it will be a basis for that subspace. And I just randomly chosen this element. I could have chosen, like, not this one, because this is 0. I don't want that, but I could have chosen this one, and this would give me what? -4. -8. So that's also a basis element. I could have written -4, -8. That's fine. Tamam mı? Başka sorusu olan var mı? Peki. Okay, now we will pass to so-called exterior product and determinants and so on. Determinants and exterior product are basically the same thing, and again they are just as I told you before, determinant or exterior product are just signed areas or signed volumes, signed lengths. Okay, and first I'll give you an idea why that's the case. So, chapter 2, exterior product. This is a special tensor product. Okay, this is a special tensor product, but first, it won't look like a tensor product at all. First, let's talk about two-dimensional as a motivation. Two-dimensional oriented or signed orientation is a general concept in mathematics. It's very important object, orientation. But orientation basically comes down to a sign. Okay, well, zero-dimensional orientation is maybe a sign. We have several different kinds of orientations, right? Right hand rule, we say counterclockwise orientation, right? If you are on a line, orientation is just an arrow, this one and this one. On the plane, we have two orientations, counterclockwise or clockwise. In our tree, we have right hand rule and left hand rule. Each one gives an orientation. So we have basically two orientations on each vector space. Okay. And areas, lengths comes with orientations. Why is that? Because physical quantities comes with signs. You know, you have work done, but depending on who did the work, it can be plus or minus, right? Charge, electric charge can be plus or minus. So physical quantities corresponds to lengths, areas, volumes, but they have usually an orientation. If you have let's say region in the tree space, and you want to know how much, let's say, suppose there are holes here, and how much air flows through this region. It's a real number, but it can be positive or negative, right? If it flows this way, you may call it positive, and if it flows this way, you can call it negative. Okay, so physical quantities comes with usually signs. Therefore, you know, mathematical quantities naturally should come with signs. You don't just consider this as an area, but it's area, but with an orientation. You specify which direction is positive, this direction or this direction. Okay. Now, and we will see now why orientation comes naturally if you are trying to find area of a, let's say, parallelogram. Okay, now in 2 dimensions we are going to study areas, but let's make the following assumption. Okay, if I have a rectangle of sides A and B, let's say the area of this rectangle will be this. But I'll be actually cautious. I'll say plus or minus. Okay, and later we will see why we should be careful. Okay. Now let me define the following function. Define the following area function. Okay. If you give me 2 vectors in R2, so this is a vector in R2, this is another vector in R2, A, B, B. Suppose this is the area of the parallelogram, right? It's a real number, parallelogram. Determined by the vectors U and B. Yani burada yine tabii ki bir assumption'la başladık. Right? Here I started with this assumption. It is something nobody would object, right? Area of this is just A times B. But it can be plus or minus. We will see why we should be cautious. Okay. So, if you give me 2 vectors, U and V, we form the parallelogram, and AUV is the area of this figure. Okay. Well, what do we ask from A? We ask the following properties from İlki şu. If I increase the one of the lengths of the parallelogram by some number, then the area should be just multiplied with the number, right? So if I increase one side of the parallelogram, multiplying that side by lambda, then area should be multiplied with the same number. Meaning this. So suppose this is U and this is V. I have this parallelogram. And then I have lambda U. So this, I have this area and this area, and we assume that A should satisfy this identity. Değil mi? Yani bir kenarı 2 katına çıkartırsak alanda 2 katına çıksın. Değil mi? Gayet masum bir istek. Yani şey. Tabii bunu diğer kenardan da istemeliyiz. So this should be also equal to the following. U lambda b. Right? Bu tanıdık geliyor mu? Değil mi? Bu lambdayı buraya da koyabilirim. Buraya da koyabilirim. Değil mi? Tensörlerdeki şey, başka bir şey değil. Yani böyle masum görünen kabullerin, isteklerin nelere mal olduğunu göreceksiniz. Okay. İkincisi şu. So first one is this. Second one is the following. If U and V are parallel, or if U and V are the same, then A U is the same. What is it? Well, one side is this. One side is the parallelogram, and the other side is the same. So U and V are the same. So the parallelogram is just a piece of line. What is the area of this? 0, right? Okay. Third one is this. If U and V are two vectors in R2, and lambda is a real number, then area of U and then V plus lambda U is the same as area of U and V. So if I add a multiple of one side to the other side, the area doesn't change. It looks strange, but it is something very natural. What is it? Let's see. Suppose this is the vector U, and this is the vector V. Okay. And I have this parallelogram, right? Area. So area of this is just AUV. What about this guy? Well, I have to add to V a multiple of lambda. Let's say lambda U is this vector. Lambda U. I'm sorry. Now we add lambda U to V. Lambda U is this vector plus V. What is the result? After you add two vectors in R2, you take this vector and put it here. Right? So this one here is just like this vector is V plus lambda V. Right? And then I ask the following. This is my first vector, and this is my second vector, and we form the parallelogram formed by these red vectors. How would you do that? Well, you take a vector parallel to this one, starting from this, right? So you form this vector.
Hocam U ve şeydir almıyor.
Efendim?
U ve boyu alır.
D artı lambda U. Tamam.
Boyu ve vektör altı. Birinci vektör.
Ha, U'yu. Ha, özür dilerim. U'yu alacağız. Özür dilerim. Tamam. Tamam. U'yu alacağız.
Yani şuradan alacağım değil mi? Evet.
Öyle değil.
Okay, so we have to form this parallelogram. U, B plus lambda U. U is this vector. U is this vector. And U, B plus lambda U is this vector. So what we do, we form this parallelogram. Right? And area of this. Bunların alanları aynı mı? Right? This parallelogram and this parallelogram, the brown one, has the same areas because they have the same base length and the same height. Right? The heights are the same and they have the same base length. So these are the two pictures.
Okay, let's have a break. After the break, I'll continue.